All right, this could be kind of a complicated equation, um, a complicated lecture, I guess. We're going to try to derive an equation um, for the wave, for a wave equation. And so we have a wave, that looks like this. And I want to get an equation for this wave that would tell me what the y position of a particle on this wave is at any given time. So, so for right here, the y position is 0, but then here it's positive, and here's a maximum, and here it's 0 again. Then it actually goes, the y position is negative as you go up, maximum and a minimum. And I want to try to derive kind of an equation for that, if we can. So this is related to the unit circle. If you remember, a unit circle has a radius of 1. We'll call it 1 meter. It's 1 unit. So we like to use meters for our units. So 1 meter. And if you think about that, by the way, what's the diameter? Exactly. That's right. Diameter is the actual right answer. Diameter. Di means 2 meters, right? So that's why it's called the diameter of a unit circle, is actually because it's 2 meters long. A meter, diameter. Okay, amazing. You're just amazed by that, aren't you? Okay, so if I take a unit circle and we start here at 0 degrees and I start angling this around and I get something like this, and if we look on this little graph here that we have, so I have it at 0 and I could start bringing it around here, then you see that and what we're going to do is we're going to graph this. Instead of having just be on the unit circle, we're going to graph it over here on this graph. So on the y-axis, I have the y position of how far it's going up or down. And then on the x-axis, we just actually have the angle. So if I want to find this y, where this is at the y position, I could look at this angle right in here, and it'd be the sine of this angle would be this opposite side over the hypotenuse. And what is this hypotenuse? Well, the hypotenuse is 1. So so this y value is actually the sine of the angle. The sine of the angle would be this over 1, so it would just be this. Sine of the angle would be this y value. And see, this is how we can generate a sine wave. See, I can go all the way up to right there. I'm at a maximum at 90 degrees, right? And then come back down, and then there's at 180 degrees. Okay, I have a y value of 0 again. Then I go down to 270 degrees, and I have a minimum of -1, and all the way back to 360. And see, I have a whole wave. So a wave, one whole wavelength, and remember a wave consists of one crest and one trough. So one wave can be generated by basically going around a unit circle one time. Okay, so that's kind of important. So as we go around and around and around, and if I go faster and faster and faster, I'd have a higher frequency. And I wish you keep just generating a wave all the way out, because we went around 2 pi. This is starting over again at 0, but technically you go to 2 pi, and then you're at 4 pi, and then 6 pi, and so on. You keep a wave going. Okay. So the sine of, so right here, to get back on this one, to get the sine of that angle, it'd be opposite this right here over the hypotenuse. So y equals the sine of the angle. That's kind of how we're starting our wave equation with. Okay, how would what would happen if I had instead of a unit circle, I had a bigger circle, right? A bigger circle with a bigger, like 2 meter radius. Well, what would that do on my graph? That would just make the that would just make the wave, taller, right? So this radius is actually the amplitude. The radius is actually the amplitude. So I had a unit circle, had a radius of 1, I had an amplitude of 1. How is that gonna change our wave equation? Well, the y, if I had a radius of 2 on this circle, then my y is going to be 2 times greater. So I have y equals, what I want to do is I want to put a coefficient out here of amplitude times the sine of the angle. Okay? All right. So we've started. All right. So now it gets a little complicated. What I want here for my circle when it's going around is I don't want this x-axis. So this is my y. My x-axis, I actually want to be time. We always kind of want to graph things versus time. So I want this x-axis to be time instead of just the angle. So how can I get time into this thing? So instead of, I want to know how fast this thing is going. I'd like to know how fast this thing is going around. Okay, so if I'm going to have this be graphed against time, then we're moving around, through certain angles, in a certain amount of time. What is that? What is that? Moving around through angles in a certain amount of time. That is angular velocity. If you remember, angular velocity is how much angular displacement over time. It's how much angular displacement you move over time. So what is the angular displacement? It would be the angular velocity times time. How fast it's spinning around that circle times the time. So my equation is going to look a little different here. A times the sine of angular velocity times time is how fast it's going around that unit circle. Okay. Now let's think about that. So it goes around this circle. Let's say we have this circle and we go around, one time. Okay. What was the angular velocity? How do you find the angular velocity of how fast this thing went around a circle one time? Well, how far did it go around one time? Well, it went 360 degrees or 2 pi radians, right? 2 pi radians. And how much time did it take to go around this thing? Well, a certain amount of seconds, okay? But we call the amount of time it takes to go around one time, one cycle, we call that the period, right? It's the period. So instead of in for angular velocity, let's take this a little bit further. So angular velocity would be 2 pi over the period. Can't write on there anymore. So angular velocity equals 2 pi times 1 over the period. What is 1 over the period? 1 over the period is frequency, right? So the angular velocity is 2 pi times the frequency. So I can put this in for my angular velocity, right, in this equation over here. So y, the vertical displacement, is a times the sine of 2 pi f times t. And that will give me my y position. Okay, one more thing I need to add in here, because right here we started at an angle of 0 degrees, but we might not start there. We might make a wave starting like this instead. We might start at 90 degrees. We might have a different starting angle. So we need to actually add a starting angle in there. Normally it's 0, and so this equation would work totally fine. But really the final equation, our wave equation, is y equals a, the amplitude, times the sine of 2 pi frequency, the time, plus phi. Phi, if you remember, is like the phase angle, the starting angle. Okay, so this is our equation, our wave equation. If you didn't understand all that coming up to that, I'm sorry. I tried to do my best I could, but in the end, we need this equation to figure out what's the y vertical position on a wave at a given time, down this wave, somewhere, maybe 40 seconds down this wave. What is the y position? And we need to know, of course, the amplitude of the wave, and we also need to know the frequency of the wave and the starting angle of the wave, and we can figure out what the y position might be. Okay. All right. Good. So we have a problem in the book 6.4. It says, what is the vertical position of a medium? And that of course is y. What is the vertical position of a medium particle in a wave at t equals 3 seconds that has an amplitude of 45 centimeters and a frequency of 4.70 hertz with a starting phase angle of 190 degrees? Okay, so I'm going to rewrite the equation for us here. So we had y. Whoops, let's see, we had y equals, we had a times the sine of 2 pi ft plus the starting phase angle. Okay, now all of this stuff in the parentheses, that needs, so we've had all year long, we've talked about, is your calculator in radians or degrees? Okay, so in this one, you can have it in either one, but that means that everything in here needs to be in radians, okay, or it all needs to be converted to degrees. So this angle, this phase angle right here is starting angle is 190 degrees. So if you wanted this whole y to come out be correct, you need to take that 190 degrees and you need to change it into radians before you put it into here. Okay, I can rewrite this equation. I can do it like this: y equals a. I don't know why my y equals a times the sine of, instead of 2 pi, I could do 360. I could do 360 degrees, ft plus the starting angle. Okay, I could do it this way. I could write the equation either way. Okay, if you want to leave your calculator in degrees, then go ahead and use this equation and put in degrees for the starting angle. Or if you want to leave your calculator in radians, you could use this equation, but this starting angle here needs to be in radians. Okay, so either way will be fine. Depending on, I like to leave my calculator in degrees, so I would always be using this wave equation. So let's solve this particular problem. Y would equal the amplitude, and the amplitude is 45 centimeters. That needs to be in meters. So the amplitude would be 0.45 times 360 times the frequency, and the frequency is 4.70 hertz, 4.70 times 3 seconds is the time, okay, plus the starting angle, and since I'm using this equation, I can leave it at 190 degrees, okay, and that would be it. So if I plug all that in, I totally forgot my sign there, so I'm going to rewrite that again. Y equals 0.45 times the sine of 360 times 4.70 times 3 plus 190. Okay, and that y, if you plug all that in, I got like a negative 32 centimeter. It's like a negative 0.32 something meters. So it'd be negative 32 centimeters was my y position. So it's on the downward drop in a wave. Okay, it'd be negative 32 centimeters down. So we can use this equation. We're going to use this equation. I think I'm going to do some lectures on actually how to graph some waves in Google Sheets. I thought that might be kind of a fun online thing to do during this coronavirus. So anyway, these are the equations you can use. These are the wave equations. This is the one you're going to use if you want to keep your calculator in degrees, and this is going to be the one you'll use if you want to have it be in radians. But if it's going to be in radians, that starting angle phi needs to be in radians. Here, the starting angle phi would have to be in degrees, so it depends on if you want to convert or not. Okay, so that was a big, long thing for the wave equation. Hopefully it made somewhat sense.